So for problem number 1 on optimization worksheet number 2, we're trying to find the points on the parabola here, the function y equals 6 minus x squared, that are closest to the point 0,3. And it's really helpful in problems like these, optimization problems. We're trying to figure out is closest to. So first of all, we want to draw a picture of it, of the situation. And then once we draw a picture of the situation that's going on, we can identify a function and try to minimize. So the closest to means we're going to minimize something. So the parabola, if we graph it, it's got a vertex of 0, 6. The equation for the parabola, y equals 6 minus x squared. And then we have this point halfway from 0 to 6 at 0, 3. And that's the point in which we can draw many lines from this point to the parabola. It looks like somewhere over here on the parabola in the first quadrant, and then also, since parabola is symmetrical with respect to the y-axis, then we would find another point that was the same distance from the point 0, 3, and that distance being a minimum. So that's what we're trying to do, is we're trying to minimize the distance, and let's call that distance d. We'll just use this distance because the other distance will be the same. So we'll just find this distance here from 0, 3 to the parabola, and then again we're trying to minimize that. And so we have to figure out is, well, how are we going to express the distance in terms of just one variable? And that's one of the major hurdles to being able to be successful in figuring out how to find that actual distance, or whatever points are closest to 0, 3. So we have to create a function, and let's create just a function, the distance expressed in terms of x. And it's really helpful as well to, we can look at it like this. We're going to can draw a little right triangle there to figure the distance x. We can remember the distance formula if you want. But I find it, instead of having to memorize the distance formula, we can just kind of figure it out using the Pythagorean theorem. We can always do that. So if that's d, then the distance from this point here to this point here would be that leg of the right triangle. And so what would that be? Well, if we're strategic about this, then we'll call that x, because from the origin to this value right here, that's x. So from 0 to that point right there, that's x. That's that leg of the length of that leg of the right triangle. And then, well, how far is this? Well, the y-coordinate of that point right there will have a value of 6 minus x squared. But that's not the length of that leg of the right triangle, because that leg doesn't go all the way down to the x-axis. How do we figure that out? Well, from this point to this point here, we know it's up 3, so we go up 3, and then we know that the total distance is 6 minus x squared. Then the distance from here to here would be 6 minus x squared minus 3. So this distance is 6 minus x squared minus 3, and you can see why it's not necessarily the calculus that causes students to not be able to get a calculus problem right. It's really the algebra involved in these kinds of problems. So the algebra involved is finding the lengths of these two legs of the right triangle and expressing the distance here of let's say this hypotenuse of this right triangle in terms of x. And so let's simplify this a little bit. 6 minus x squared minus 3 is equal to 3 minus x squared. So the grand scheme of things here, the length of that leg of the right triangle is 3 minus x squared, and the length of this leg is x. And so the distance then, distance squared, would be the sum of the squares of the other two sides. So x squared plus 3 minus x squared squared. And if we take the square root of that, then let me scoot it up a little bit here. If we take the square root of that, then we get the actual distance. So the square root, and let's simplify this a little bit. This is 3 minus x squared squared would be 9 minus 6x squared plus x to the 4th power. And if we even simplify that, we get the square root of x to the 4th minus 5x squared and then plus 9. So that's the distance in terms of x. So we have this distance. I'm going to use some of this space over here to the right. So the distance in terms of x is the square root of x to the fourth minus 5x squared and then plus 9. So that right there is the function that we are going to try to minimize. So all that being said, we have a function. How do we find a minimum value for a function? Well, the minimum values happen at endpoints as well as critical points. Now, the distance, if we think about this, the distance in terms of x, that's going to be a positive number. So no matter where we plot a point on the parabola, if we calculate the distance from that point to the point 0,3, it will be a positive number. So the distance is always positive. That's a good thing to know, because we're never going to have a time when we have to worry about negative values for the distance and things like that. So that's going to be really helpful. But how do we find a critical point? Well, we always have to find the derivative. Let's express the distance in terms of x as something to the 1/2 power. So that's to the 1/2 power, and then the distance, the d prime. So we always have to take a derivative, and we set the derivative equal to 0. The derivative is 1/2 times this stuff, plus 9 to the negative 1/2, and then multiplied by the derivative of that stuff. And the derivative of that stuff is 4x cubed minus 10x. That's the derivative. And then if we simplify that a little bit, how are we doing over there with space? We're good. So if we simplify that a little bit, d prime is equal to, we're going to factor out a 2x out of that. So we're going to take a 2x from this polynomial, and we were left with 2x squared minus 5. That's in the numerator, and then in the denominator we have a 2. We also have this polynomial to the 1/2 power, but let's actually write that as 10 times the square root. Square root of x to the fourth minus 5x squared plus 9. And here's the other thing that it's good to know. I mean, good to think about. This guy right here should look familiar. That's the distance. That's the distance between the point and the point 0,3 and the point on the parabola. Well, if that's a distance, that's going to always be positive. So you don't have to worry about setting that equal to 0. All you have to be concerned about is, well, what happens when would the derivative be 0? Well, it's only when the numerator is 0. Well, it's 0 when x is 0, but x equals 0 doesn't make any sense because, oh, I guess it does. Because if x is 0, then we have 3. The distance would be 3. So that's okay. However, that's probably not going to be where we're going to have the minimum distance, because just based on what it looks like. But we have d prime equals 0 when x equals 0, and when x equals, let's see, 2x squared minus 5. So let's write that 2x squared minus 5 equals 0, or when 2x squared equals 5, or when x squared equals 5 halves, or when x is equal to the square root of 5 halves. And the square root of 5 halves, if we multiply top and bottom by 2, we have the square root of 10 over 2. So plus and minus the square root of 10 over 2. That's going to be our magic number. And when we get that number, we have our d prime test. D prime test. We have 0. We have positive radical 10 over 2. We have negative radical 10 over 2. And think about radical 10. It's a little bit more than 3, so it's about 3 halves, 3.1, 3 halves, so it's more than 1.5. And so let's pick a test value of 1. If we plug a 1 into d prime, trying to find the sign of d prime, well, if we put a 1 into d prime, where do we find d prime? Right here. So this is our d prime right here. That's the one we're going to plug it into. If we plug a 1 in, the first factor is positive. The second factor, 2 times 1 squared, that's 2. 2 minus 5 is negative. So we have a positive times a negative. Remember, the denominator is always positive. And therefore, it's negative. It, meaning the d prime, is negative on the interval from 0 to radical 10 halves. We could put a negative 1 in there. If we put a negative 1 in, then that would be a negative times a negative. That's a positive. Up on top, so we have a positive, positive, positive. Remember, 0 is when d prime equals 0. So that's a max. That's a max right there. So we have we go from positive to negative, we have a max. So the distance between, so we have a maximum value, local maximum. If x is equal to 0, there's a max. And then if we pick a value like 5, well, if we plug in 5, we get positive, 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 so therefore positive. And therefore d goes from decreasing to increasing, and therefore we have a minimum right there. So, and then we're going to have the same thing over here. Negative 5, it's going to be negative, so it's going to be negative, and we're going to have another minimum. And so therefore we have a min, a max, and a min. And the mins are going to happen when x is equal to radical 10 over 2. And if x is equal to radical 10 over 2, it says which points? Well, we then have to figure out, well, what's the y-coordinate? So we know we have a min when x is radical 10 over 2 or negative radical 10 over 2. And if we have a min there, we have to figure out, well, what's the y-coordinate? Well, the y-coordinate is equal to 6 minus the x-coordinate squared, and that's 6 minus radical 10 over 2 squared. And so that's 6 minus 10 over 4, 6 minus 5 halves, and that's 12 halves minus 5 halves, so that's 7 halves. So therefore, the points are, and based on all the explanation here, the 2 points are radical 10 over 2, comma 7 halves, as well as negative radical 10 over 2, comma 7 halves. Those are the 2 points in which that are on the graph of y equals 6 minus x squared that are closest to the point 0, 3.